All right, so we're going to look at another kind of application of derivatives, which is very much tied into the idea of the derivative as the slope of the tangent line. These are called linear approximations. And I think that you'll find that a lot of these applications are a little bit old-fashioned because we have pretty sophisticated calculators, but I think it's important to understand the idea of linear approximations because this technique is used in a lot of software in order to handle certain calculations. And so, for that reason, it's good to understand these ideas. So the idea of a linear approximation is this. We're trying to approximate some function of x when x is near some value a. We're going to find the tangent line, which is in the form y equals f of a plus f prime of a times x minus a. So if x is close-ish to a, then f of x is going to be close-ish to f of a plus f prime of a times x minus a. And so we call L of x equals f of a plus f prime of a times x minus a. We call that the linearization of f at a. So let's see an example. Okay, so we'll use the linearization of this function f of x equals square root x plus 3 when a equals 1 to approximate a couple of square roots, square root of 3.98 and 4.05. So the derivative f prime of a, right, this is what we're going to need. This is going to be 1 over 2 square root of a plus 3. And for us, f prime of 1 is going to be 1 over 2 square root of 4, so that's going to be 1 over 4. And so the linearization of x is, what is f of a? That's f of 1, that's the square root of 4, which is 2. So it's going to be 2 plus 1/4 x minus 1. It's just to say how far away. So when we're trying to approximate square root of 3.98, in this case, since x is going to be 0.98, right? And so the linearization of 0.98 is going to be 2 plus 1/4 times, actually let's put it as at 0.25 times how far, what's 0.98 minus 1? It's negative 0.02. And so you work that out. So you get 2 minus 0.005, which is going to be 1.995. Incidentally, the square root of 3.98 is comes out to be 1.99499, and that it's pretty close to 1.995. Let's take the second one for the square root of 4.05. In this case, x is going to be 1.05, right? So the linearization of 1.05 is going to be 2 plus 0.25 times 0.05. That's 2 plus 0.0125. So this is 2.0125, which is pretty darn close to the square root of 4.05. Now, you're probably thinking to yourself, this seems like a lot of work in order to do something I can do in a moment in a calculator. Yes, this is just to illustrate what these linearizations are. In practice, of course, these are going to be much faster to do in a calculator and more precise. But that's not really the point here. The point is to understand, so the point of this is, I mean, there are functions out there that would be almost impossible to work with without making linear approximations of them. And so while these are pretty easy to calculate, there's much more complicated things that you will probably encounter at some point, and you might need to use this technique. So I don't want you to think this is totally useless, but it may seem so for a simple example like this. So now let's look at how accurate this approximation is. So we want to ask, for what values of x is this approximation square root of x plus 3, 7/4 plus x over 4. This is just what the linearization we had on the previous example, just written in fractions. For what values of x is this accurate within 0.5? Which is to say, we want to know when is the square root of x plus 3 minus 7/4 minus x over 4, this difference, less than 0.5. And so what I'm going to do, we can write this as an inequality, 7/4 plus x over 4. When is that between square root of x plus 3 plus 0.5 and square root of x plus 3 minus 0.5. So if we're to graph out this inequality, we can see that this inequality is true anywhere between this value here and this value in the x-axis. So as long as x is between, let's say, roughly negative 2.66 and 8.66, or if we wanted to be a little bit more cautious, we could say between negative 2.7 and 8.6. So we can kind of go in just a tiny bit on either side just to be extra cautious. But as long as x is, which is actually a pretty wide range in order to get this close of approximation. But you can see visually that the linearization does work pretty well because the function itself is not too nonlinear in this range. So we'll talk about differentials. The differential is this dy is f prime of x times dx, which we can put in terms of in terms of a picture, where if this is the function f of x, and this is a point that we're interested in, if this is a distance dx, right, and we're going to draw the tangent line. So where the slope of this line is f prime of if this is the value x, like right here, call it a or whatever. If you take the slope and multiply it by dx, what you're going to get is your dy. So this is the differential. This is the height from here to here. So dy over dx is f prime of x, right? Now there's another concept which is called delta x. So if this is a change in x, delta x is the change in the y value. So I'll put it on the other side. This is our delta y. As when x, so I'll put it in terms of notation. Delta y is f of x plus delta x, so for some change of x, minus f of x. So delta y would be the actual change of the function when x changes by delta from like some starting value. Here we're fixing x. So dy, this differential, is kind of like an approximation of the delta y, but you can see how it's going to be off. The larger dx is, or delta x is, the more these two are going to differ, right? So you could think of the gap between them as some sort of an error of approximation. You can think of it like that. Okay, so the radius of a sphere, 21 centimeters, with a possible error in measurement of 0.05 centimeters. We want to know what is the maximum possible error in the calculated volume if we're using 21 centimeters to calculate the volume. Now remember that the volume of the sphere is 4/3 pi r squared. So the volume is 4/3 pi r cubed. And so what we want to use a differential for the radius, a dr of 0.05. We want to find the differential for the volume. So we're going to take the derivative using the chain rule. So dv is 4/3 times pi times 3r squared dr. Well, the 3's cancel. And we're going to be plugging in then. We have 4 pi times 21 squared times the 0.05. And this should give us this estimate for the differential for volume. And so that's going to come out to be roughly, I'll approximate it to roughly 277 cubic centimeters. And this would be the maximum absolute error. The relative error can be found by dividing this by the volume at 21 centimeters. So that would be 277 divided by the volume for 21, which is to say 4/3 pi times 21 cubed, which comes out to be 0.00714. That'll be the relative error, the maximum relative error. And the percentage error, well, you just move the decimal place 2 places over to the right, so it'll be 7.714%. So although that seems like a large absolute error, it's good to put it in terms of how is it relative to the value that you're approximating, which it's actually pretty small relative to the volume when the radius is 21. Well, okay, I mean that's everything I want to talk about for this section. We'll do some examples, of course. We'll do some more practice, and this is going to wrap up this chapter on derivatives. Now we're going to see. We're going to look at some more advanced stuff in the next chapter, especially related to logarithms and exponential functions. So that is that. All right. Bye.